On April 17, 2026, a transmission left Earth and traveled at the speed of light for 23 hours through deep space. When it finally reached Voyager 1, its sole purpose was to shut down a piece of scientific hardware that had been running continuously since 1977. This single mechanical detector spent 49 years recording the environment of the outer solar system, mapping the transition into the galaxy before its power finally ran out. Before Voyager launched, it sat in a clean room, a massive assembly of antennae, sensors, and structural booms. The LECP instrument used a stepper motor to drive a detector across 8 distinct sectors. On the 8th step, a 2mm aluminum sunshield blocks the field of view to measure background noise, which is subtracted to isolate the actual signal. Engineers originally rated that stepper motor to survive 500,000 steps. Over the next 5 decades, it performed more than 6 million. Voyager blasted off Earth and pushed out into the dense, chaotic inner solar system. At Jupiter, the LECP discovered a magnetic field pumped outward from the inside. The moon Io was actively venting a ton of sulfur and oxygen every second, driving a massive centrifugal dynamo fueled entirely by a volcanic moon. To measure that intense radiation, the instrument had to work under extreme stress. The motor cycled rapidly, and intense particle counts slammed into the detector on every rotation. At Saturn, the instrument documented a completely different physical mechanism. The massive ring system acts like a sponge, physically absorbing the trapped particles that cross the equatorial plane. This chart plots the particle count rate against Saturn's radius. Every time the detector swept behind that 2mm aluminum shield, the count dropped to baseline. When it swung back out, it recorded steep drop-offs that precisely mapped the physical gaps in the rings. The mechanical resistance the instrument encountered in those radiation belts provided the raw data needed to calculate the massive, violent physics of the gas giants. Then came Uranus. The planet's magnetic axis was tilted 59 degrees and offset from the center by 1/3 of the planet's radius. As Uranus spun on its side, the entire magnetic field wobbled violently. For decades, the LECP data showed empty electron belts, leading scientists to think the moons were dead. But a 2024 reanalysis revealed a solar pressure wave had hit Uranus right before Voyager arrived, blowing the plasma out the magnetotail. Those moons might actually harbor liquid oceans. Neptune was tilted and offset too, but its magnetic tail was completely quiet. There were no substorms, just smooth dissipation, while the captured moon Triton exhaled nitrogen gas into the cold. Before this tour, models assumed all planetary magnetic fields were aligned with their rotational axis, like Earth's. Voyager's data forced a revision of that theory, proving that offset asymmetric fields are a common feature of our solar system. With the planets behind it, the Voyager interstellar mission began. The new target was the absolute edge of the heliosphere, the boundary where the supersonic solar wind hits the back pressure of the galaxy. Voyager 1 crossed the termination shock at 94 astronomical units, and Voyager 2 crossed it years later at 84. That 10-unit difference proved the sun's bubble isn't a perfect sphere. It's blunted and pushed inward by local interstellar forces. This is a stacked graph tracking the heliopause crossing in August 2012. The top line shows solar particles, and the bottom shows galactic cosmic rays. Over a matter of hours, the solar particles dropped by a factor of 1,000, while the galactic cosmic rays surged upward and locked at saturation. Theory predicted the magnetic field would mix and rotate at the boundary. Instead, the LECP data showed the interstellar magnetic field remains distinct. It drapes around the outside of the heliosphere, parallel to the solar field. These data points confirmed the transition. The sun had let go. Voyager was in interstellar space. Decades later, in 2026, Voyager 1 is operating in the freezing dark, billions of miles beyond that boundary. The spacecraft's power comes from a decaying supply of plutonium-238. With the reactor losing 4 watts of available power every year, the mission engineers were forced to ration what little remained. They transmitted the command to shut the instrument down. The detector head finally went dark, though the stepper motor was left slowly turning, drawing barely half a watt of power. The hardware survived the radiation belts of Jupiter and the edge of the solar system, only to be stopped by the physics of its own decaying power source. The engineering that made the LECP possible didn't end with its shutdown. The lineage continues at the Applied Physics Laboratory where it was built. The exact architectural blueprint of that mechanical detector directly informed the next generation of space sensors, including Pepsi on New Horizons and the IMAP Ultra instrument, designed to remotely image the exact boundary Voyager crossed. Right now, new spacecraft are carrying those successor instruments out into the vacuum to continue mapping the environments Voyager first encountered. The original instrument is silent, but its 49-year record provided the first physical map of the solar system's boundaries, establishing the data required for the missions that will follow it.